Yeah, welcome once again, everyone, to this new iteration of Hackware this month. And we are doing origami. Not just any origami, scientific origami. And in this case, a venture into the other spatial dimension, hopefully, in origami. So before we move on, I'd like to give a little bit of thanks to some famous faces who've inspired me inside of this work over here. Most of the folding methods that I'll talk about were created by one venerable origami engineer, probably the first ever origami engineer, Fujimoto Shuzo. Feel free to scan the QR codes. It lists the works that I've cited over here. The famous fold I'll be discussing, the famous, if you were here last time, the flat folding origami, also known as the famous Mura Ori fold, was developed by Mura Koryo over here. A new approach to non-linear creases in origami was developed by Winnie Leung. And my new approach to applying conformal mappings to origami was inspired by the individual work of Milo Brown. So let's get right back into it. So show of hands, how many of you were here last time? Oh yes, I remember that. All right, so now the first off, a little bit of math. Have you ever had this? Have you ever had an issue where you were in the office and you want to fold a big A4 sheet of paper neatly into an envelope? How would you fold it into thirds?
Just buy it.
Yeah. Yeah.
The envelope and you just fold it.
Yeah. Huh?
You just fold like
All right. Yeah. I'll repeat that for the listeners at home. Most of us would grab either end and just kind of agar smush it into an approximate S shape and hope for the best. Well, with this fancily named algorithm, you can always fold any piece of paper perfectly into thirds and also into fifths and maybe even sevenths. This would work for any sheet of paper. It even works for angles, areas, and curvatures. And all we need to do is memorize this complicated table. Now, just kidding. An improvement from last time is I've got a little mind palace method. If you all watched Sherlock before, if all of you have, if any of you were in the amateur radio league, you may have known about the apart, be a good boy mnemonic for Morse code. I tried to apply that over to the right left folding for the Fujimoto's method. So first, try and commit these to memory. It'll make sense in a bit. If you want to fold something in thirds or fifths or sevens over here, you'll have to memorize this complicated repeated binary fraction. Just bear with me for a bit. For 3, it's begin for divisions in 5s. A little rain falls, a little rain falls. 7, lucky man. In 9ths, we're now marching on. 11, the old man came to the town with pride. And 13, the hardest one. I hope this constructive criticism is accepted if this one works. 13 is a real doozy, so I try. The dark is not as deep as the light that shines through night.
Wow.
Yeah. Well, but at least that sure is better than saying 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1.
So what if you remember it as just a decimal number in binary? Or in hexadecimal?
If you can remember it, please tell me how you remember it, because I am still learning to train to clean up my memory palace.
Fair enough, yeah. I don't know. I'll keep the aggravation.
I'll keep the aggravation.
Or just you have bring a ruler with you.
Yeah. Well, but the key part of this is that you don't need a ruler. All you need is your hands and your eyes, or just feeling. So now, here it is, the fantastic Fujimoto's method once again. I've got a bunch of paper right in the middle, so feel free to go put some in your hand while you try this on. This is very much a hands-on activity.
Perfect one.
So we are trying to estimate the number of folds.
We're trying to make a perfect third.
A perfect third, perfect fifth, perfect seventh, perfect prime number, basically.
Basically a numerical approximation to a prime number.
Yep, it is. So first off, let's try something like
Can I make this fish? I'm not really.
let's try divisions in what'd you say? What's a good number?
Let's just try 3 first.
Right, threes. All right. So let's begin. All you have to do is grab your sheet of paper and then fold it right in half. This is a given for every step. You have to fold it in half. And then now that you fold it in half, you're done.
Yeah.
Just kidding.
Because 2 is 3.
This is the actually this method works for folding in half. You just bring the right all the way to left, and then you just reiterate from there. Since with begin, first you take the rightmost edge and you fold it to the last crease you made, which is right in half. So you fold it in a quarter, like such. This. You don't have to fold it all the way, only at the top to make a little notch. Well, that's good. Then you can see yourself approaching to the right crease. All right. A quarter. We got a quarter there. Simple enough. Now, we begin. We move the left side all the way to the last crease we made earlier. And then we get something a little bit like this. Yeah. And then that doesn't look like a third. We just do it again. Grab the rightmost edge and then bring it to the last crease you made. It's getting to a third. You can start to see it forming out of there. Yes? Once you move left to the last place, you make a crease over there. And then you bring right to that crease that you just made.
It's like a numerical approximation, right?
Yes.
Every iteration is smaller and smaller and smaller.
It's basically a graphical. You could say it's a graphical Newton-Raphton's method.
How did you get there?
Yeah, just ad infinitum, right, left, right, left, right, left. The great thing about this method is that every time you make a fold, you divide the error, which is how far your crease is to the actual third, by half. So as you know, that converges really darn quickly.
It's what do you call it? Geometrical.
Geometrical?
Geometric series.
Somebody series.
Yeah.
Some
It's one of it's geometric series or whatever.
Power series?
Yeah.
Zeta function? IDK.
Obviously, nobody here majored in mathematics, right?
Yeah.
You're just like guessing.
Not yet.
Programmers and people listening at home, please help me
I
out.
only recently found out about lambda calculus.
Oh yeah.
Perfect concept.
And yeah. If you want to, you can keep doing left, right forever. But as you can see, this seems to be right about there. So you pull down your crease from the top all the way to the bottom. I'm gonna push it down. Zoop. I know it's way faster, but imagine trying to fold a piece of paper into perfect 29ths. That's where it really excels.
I think your issue there is why are you folding this piece of paper?
Well, it's better to have it and not need it than to need it and not have
If you're
it.
really bored. You might as well.
Or if you're in a math Olympiad.
If you're doing a long flight and you have nothing else but magazines, inside magazines.
Yeah, I'll get to the further applications of this interesting mathematical toy in a bit. But yeah,
This feels like a math parker. Perfect.
yes,
Stand up math.
yeah,
It is perfect.
it's right about perfect.
Okay, give me more challenge.
Okay, do a 13.
13.
29.
Yeah,
Yeah, good luck on that one.
we can do that way later. We've got
Right,
more
this
time.
this does work for all odd numbers, right?
I
Yeah.
need to do a few more iterations.
Well, not just all odd numbers. It's
Perfectionist.
all non-powers of 2.
Yeah, actually it works with
Because even folding is for powers of 2. This one is used for isn't a power of 2.
You're right, it
Because
is.
Because even power of 2 is trivial. Just keep folding it down.
No, you said the magic word.
Yeah, it would work for any non-power of 2, but you could technically use it for powers of 2. That's what makes it universal.
Yeah.
So now
It's complete.
I'm sure most of you have approximately 1/3. For me, I was a bit too quick and I only did 2 iterations, but that's about 1/3, and I'm sure that'll fit in an envelope. Here's one I made earlier. This was perfect. This is perfect sevenths. Yeah, so that's really cool. Now you can fold paper into odd numbers. Now what? Well, I did a little bit of looking around on what you could possibly use such a method. I've noticed that this works for angles, for constructions, for curvatures, for areas, and I realized that it works around in many places in the office. Like, for example, you can perfectly split blue tack this way. You can pour coffee. You can pour coffee. You can possibly solve, that famous Die Hard water measuring puzzle. You can solve like a Tower of Hanoi with a similar method. And for anyone who has ever played Factorial before, you can
Oh my god, the splitter!
you can perfectly design a splitter.
An even ratio splitter, god damn it.
And I've been thinking, what if you since this thing, yes?
Idea.
Question?
Dividing a frequency by any number while maintaining 50% duty cycle.
Yes, that's a great application. And
what do you call it?
POL.
No, but doing it with only digital logic.
Yeah, frequency synthesizers, right? So they always need these ratios that you need for
Yeah.
numerator and denominator.
I actually designed a circuit for dividing by 25 for
Oh, you got to tell me about that.
I drew it on my notes somewhere.
Well,
Later.
We use
Yeah.
one for the one of the board we made.
So yeah, I did prototype this in Factorial, and I found out that it would evenly divide not only the items but also the throughput. So maybe you could make a marble computer using this method. IDK.
What you should do is make a computer that's able to make those layouts automatically based on input numbers.
Oh my god, a meta computer. Basically, all I can say is for this section, the analog arithmetic applications are simply astounding.
Oh god.
Yeah. A few more examples. Showing that it's possible with angle trisection. If y'all have been here before, it might be familiar.
Could you use it to make a musical instrument?
Oh yes.
Like dividing the
Yeah, into all the different ratios that you need for notes.
Yes. Actually, the
Because
first.
it's what is it? The space between the frets gets smaller as you
Yes,
go higher.
correct.
Yeah, it's by like
Without a ruler, that is, of course. I mean, with a ruler, everything, but that's easy mode, right?
yeah, but a ruler has only so many. Why not go analog? Actually, the original paper that described this folding pi showed how you can divide instead by an integer, but by an irrational number. But that requires some more further study because my microscope does not go small enough.
Is it by simply just following the trails of ones and zeros for the right left thing?
Right about, except there's a little bit of like trisection as well.
Actually, wait, can't you use a diverging equation in order to do that?
I haven't got to that, but if I am
Not diverging, converging equation of reciprocals to get pi. Because like there is a set of converging reciprocals that add up to pi, isn't there? That's how they approximate pi.
I think so. And a whole litany of others, but do get back to me about that because I'm really interested to hear about the series. Yeah, as you can see, this is a very enlightful yet elegant algorithm. But just moving quickly on, if you remember from my previous demonstration, if you had a big A4 sheet of paper, like say a resume, for example, how would you, or a map, how would you fold it into your pocket instead of folding it back and forth and then mangling the paper? There's this crazy fold that uses a bunch of parallelograms that allows you to do flat folding. Basically, push an entire sheet of paper neatly without changing orientation into a single packet like that. In order to fold that, we used last time we would do some folding by on the short side by 5, long side by 7, but this time we're going extra. So I automated it. In Inkscape, I got a script to create an arbitrary angle or number of Moira folds so I could experiment with. Like this is one that I just made out. It uses sharp edges and it compacts it to a stick, but it does not change the actual orientation of the obverse or the reverse sides. Suno, I haven't put this up to GitHub, but I hope to pump it into the group sometime.
Another thing on the resume.
Yeah. Yes. Quickly to the meat of this of the topic.
Idiot, no, you've gone too far this time.
I thought in separate research I was playing around with like complex analysis, Riemann hypothesis checking, zeta functions, Dirichlet theorems, and I thought, wait a minute, what instead of folding space and time using these mappings, what if I applied that to the venerable Moira fold? So, inspired by the work of the late Robert Lang and Milo Brown that we saw from the first page, I threw together a little Python program to wrap the basically fold the space-time of the of the A4 paper into something that is that locally preserves function, but it alters the angles and the lengths completely. So in that way, I guess you can say it's not conformal, but I'm pedantic about that. But if you fold this, thanks to the lovely use of computers, you would get a hyperbolic protrusion like this. And if you kept going, you could fold it up into an infinitely tight rod. However, my printer can only go so far, so it would, of course, stop somewhere. But if this was done, in an ideal world, I could probably get an asymptotically infinitely sharp point using this method. Basically, a knife that is infinitely sharp that you unfold into a regular sheet of graphene, maybe, or hypothetical solid.
AlphaFold looks a bit different today.
AlphaFold?
The protein folding.
Yes, protein folding. That's another cool. Imagine if you could fold proteins like origami. So yes, I only recently found out that out of all the conformal maps that I've made, some of them were foldable and many of them require actually breaking space-time in order to fold. So much more research is required over here. This is for a little bit for later. This is the method on how you would use Fujimoto's method in order to fold the Moira fold. Yeah. It's a division of a sheet by 5 and then by 7, but the folds are oblique. So we will get to the practical section later. But now for all the people at home, if you have no paper, no problem. Thanks to the power of computers and web apps, there is this absolutely amazing web-based real-time physics simulator for origami called Origami. Oh, I didn't put the name, darn. If you scan that, it will bring you to origamisimulator.org. It's amazing. It accepts SVGs.
Huffman bubbles. Is it the same Huffman that did Huffman encoding?
No,
There's two different Huffmans now.
no, but it sounds like Huffman is very has some normative determinism that they would be really smart at mathematics.
I mean, Huffman encoding is mathematics. It was used for computer science. I think it was error correction. No, it was compression.
Compression.
Yeah, it was the Huffman encoding. Yeah.
Really cool.
I mean, compression and origami are kind of tangentially related.
Oh yeah, you could map. I bet you could map information onto one of these folds and then
I mean,
fold.
every unique fold is its own value.
Exactly. That's the real essence. So the real power of it is that you can make a simple set of red and blue lines like this. It's-
Fold it without
It's
fail.
instead of having to fold it by hand, I printed this out actually and I tried to crease it and it was not impossible. So I said, screw it, I'm just going to throw it into the program. I'm going to do a demonstration afterwards on how pretty it is. The best part about it is that it will color code parts of the faces that experience the most strain. So if you want to use it for civil engineering purposes, then this is basically perfect for that. Right. This was a bit of a short one because I want to leave more time for actually playing around with this stuff. All the QR codes were created with this QR code that leads to the Disenchitify project, which is a strange name, but it's a collection of developers trying to take back needlessly monetized services on the internet and then make them basically free for all and not lead to a middleware. They are actively accepting developers, so if you have a needlessly paywalled app that you would like to make forever free again, feel free to contribute over to the
To the project.
Make Better Again project.
You know, one that definitely could use it, random.org's app.
Random
They
dot-
recently paywalled all of this stuff except the coin flip.
No.
For some reason, I don't know why. I came back to it and I saw, oh, you have to pay for this. The dice roll, you have to pay for the card, the deck of cards. I don't know what. For a randomizer.
I guess they're monetizing entropy right now. Yeah. So, that comes to the end of our the theoretical section. Now, here comes the real meat of it. I printed out a bunch of cool origami examples, and now's the time we learn to fold space and time, but only in paper. Thank you, everyone.